In section 7.4, we are finally using the Lagrangian in an example with a stationary function. So now, how do we set it up? Well, first of all, I want to show you the Redcon example. I want to go through all the problems. And we know from previous chapters that the force is equals to the negative, the gradient of the potential energy, which it will be in terms of R and T. And of course, Lagrangian is equal to the kinetic energy minus potential energy. So now, as you can see here, we have a ball moving in a two-dimensional plane, and from point 1 to point 2. And it's going along this path, this small RT path, this green path. And that is the shortest path. But actually, you can also show that it doesn't matter what path you take, the Lagrangian will always give you a stationary value. So I drew another path, this red path, and every single point on this red path is equal to the initial path plus a vector epsilon. So we can say that capital R T, of course, is equal to the initial path plus this displacement path. Let's go like that. Okay? And of course, if we go back and write it into our Lagrangian equation, we want to prove that whatever path we take, we're going to find that it's the same. So we can say that our stationary path should be equal to the integral from t1 to t2. So from the time in which the ball is at point 1 to the time at which the ball is at point 2 of our Lagrangian in terms of dt. So now here we would have two different ones. So I'm going to call the stationary for the small r, which would be the same thing, but I'm going to write the unit of measurement for Lagrangian, which would be small r dot t. And then we would have the same thing for big R. So the only thing we have to change is going to be the R, which is going to be a big R. Nice. Okay. Now, if we're saying they're the same thing, it means that the difference between the two of them will be equals to 0. Right? So that's the difference in these two paths. Now, the book calls it a little bit differently. The book calls, the book even writes it a little bit different. Now, since we know it's a difference, we can also say that S capital R minus S small r is equal to 0. The same thing. So now, the book calls it a little bit different. It calls it this S and this S naught. S naught because it's of course the initial path, the one we know is stationary, and S because it's the path that we want to prove. So now we want to prove that this is equals to 0. How do we do it? Well, why don't we start plugging this in? We know that this one minus the other is going to equal to 0. So we're going to have this one minus the other stationary path is equals to 0. Actually, I need to erase this. Okay. Right, so we can see that it's pretty much the same integral because it's same limits and same terms which we integrate. But I want to do something first. We know that L is equals to T minus U. So L in terms of capital R dot T is going to be equals to 1/2 M capital R dot squared minus the potential, which is in terms of R and T. Instead, our Lagrangian in terms of small r, so small r dot and T, it's going to be equals to 1/2 M R small r dot squared minus U, here will be in terms of capital R, of small r T. Okay, so as you can probably already see, we know that capital R from this part over here, capital R is equals to small r plus this epsilon. So I'm going to go ahead, first of all, let me write this once. I'm going to go ahead and rewrite these two together. That's what we have at the beginning. And of course, we know it's going to be the integral of this t1, t2, everything in terms of dt. Okay, and I want to substitute, instead of using capital R, I'm going to have small r plus epsilon naught. So plus the epsilon, sorry. So I'm going to rewrite this first one as 1/2 m. Instead of r dot, we're simply going to have small r dot plus epsilon dot squared minus u of small r plus epsilon comma t minus 1/2 m small r dot squared minus u of small r t. Everything is, and this is the integral from t1 to t2 of dt. Okay, so now we're gonna actually take some things that we have in common. So here we can see that we have a 1/2 m and 1/2 m. So I'm gonna write it as 1/2 m, and then what we have inside is r dot plus epsilon dot squared minus r dot squared minus, and then we have the same part here, so we have always u, which is going to be equals to, it will be minus here, because we have a parenthesis like this, so it actually would be plus right here, if I'm not mistaken. No, it would be minus, yes, I was doing correctly. It would be minus for this, and of course minus, I'm going to collect in front, u of, in this case we have r plus, epsilon, plus r. Should let me write it a little bit better. We would have something like this. Minus, I'm going to collect in front, and we have u of r plus epsilon t minus u of r comma t. Okay? And everything, of course, is still integral from t1 to t2 of dt. So from the first one, I'm going to square, I'm going to keep the math very, I'm going to show every single part of the problem. The r dot squared plus epsilon dot squared minus, plus 2 r dot epsilon dot minus r dot squared minus, and then this part is going to be the same. But one thing that you can remember actually is this part over here. So we know that a function of, for example, let's call it r plus x minus a function of r is equals to the x times the gradient of our function. Okay. We prove this by the very first calculus base. So we know that f of a function x plus h minus f of h over h is equals to the derivative of this function, which in our case would be the gradient of the function. So if we multiply both sides by h, we will find that. And we also know that in our case, our x is equals to our r, and our h is equals to our epsilon. So if we write this in terms of what we actually have, let me go on the next page. Oops. I'm going to have the f of r plus epsilon minus f of r over epsilon is equals to the gradient or derivative of f. Then we'll multiply both sides, so we're going to keep f of r plus epsilon minus f of r multiplied by epsilon, so we get rid of the epsilon at the bottom, so we'll have epsilon times the gradient of f. So this part that we have right here can be substituted and be put as epsilon times u of, times the del times our function u. So we're going to write this as epsilon times del of u, everything dt, from t equals to 1 to t equals to 2. So here we can raise our r dot squared, and out of here we obtain that it's going to be equal to t1 times t2 of, we multiply it, so we're going to get m r dot epsilon dot plus, and this is the part that actually the book tries to avoid, it's going to be 1/2 m epsilon dot squared, that the book calls, actually calls O of epsilon dot squared. Just means all the terms of which we just have epsilon dot at a higher power than 1, and then minus epsilon dot times the del times u in terms of dt. Now we could integrate this, and we can find, of course, that actually first of all I'm gonna take this part over here, duplicate it over here, take this part over here, duplicate it again. So we get rid of this part because it's a higher power than 1. So, and we want only power of 1. But actually, if we think about this, we go back. We know, we'll prove it at a better point. We know that if we integrate this at point t1 and point t2, and we go back to our drawing, we know that this vector here is equal to 0 as well as here. So at point 1 and 2, this vector epsilon is equal to 0. So this part here is going to be equal to 0 at t1 and t2. So we can simply erase it. So we have this part left here. And what I want to do is collect what we have in common. So the interval from t1 to t2 of epsilon dot m r dot minus, sorry, 1 second. Okay, here there's no dot here, sorry, so what was my mistake? I can only collect a epsilon, and I have to give the other dot to the r. So minus the divergence, not the divergence, the gradient of u in terms of dt. But as you can see, this one here is equals to a force very clearly. And this is equals to what we just proved at the beginning, as you can see right here. So another force. Oops, okay. To another force right here. Okay. Now, what is the difference in these two? Well, these two is going to be the force at the total force, so F net force of this, which is going to be equals to the constraint force, which is equals, for example, to the normal force of the plane on the ball, plus all the external forces. And then this one instead is just simply going to be equals to the external forces. So if we rewrite this, and we'll stick our negative in front. Sorry, I forgot to do that. I'm going to write this plus here. We're going to get that negative of this interval from t1 to t2 is equals to the epsilon times, well, what we have here, we have these two, sorry, actually, this one, the gradient of this is equals to a negative force. So here's going to be negative, okay. So if we add this together, we can see that we get rid of this force, and we have this times force constraint, which is equal to the normal force, for example, dt. Now, one thing that you can notice is that these two forces are actually perpendicular to each other, because if we go back, our epsilon vector is going to be parallel to the plane, while instead our normal force is going to be perpendicular. So this one is going to be parallel to plane, and this one is going to be perpendicular to plane. So a dot product of two forces that are perpendicular to each other, so it's called force 1 and force 2, or this actually vector, sorry, let me just, the dot product of two vectors, because remember these two are always vectors, always pointing in a direction. So the vector 1, for example, I'm going to call v1 dot v2, and now the v1 is perpendicular to v2 will yield 0, because we could rewrite this as v1 absolute value times absolute value of v2 times the cosine of the angle between two of them, and we know that the angle is equals to 90, so the cosine is going to be equals to 0. So this part here actually yields a value of 0. And so this difference in the stationary that we tried to find actually equals to 0. And as we said, we proved that it's going to be equals to what we said at the beginning, these two paths. The Lagrangian doesn't care what path you're taking. It's always going to give you a stationary value.